First off, at this time, I'd like to welcome Phil Gates. Phil is the Business Development Director at Gross-Wen Technologies. First off, at this time, I'd like startup, revolutionizing the wastewater Business Development Director. Since its founding in 2014, First off, at this time, I'd like Gross-Wen has attracted international attention and is poised to one day potentially be the gold standard in wastewater treatment. So please join us in welcoming Phil, and we look forward to learning more.
Yeah, thanks for having me. I'm going to start a timer because I've been told I'm on a very strict schedule here. But thanks for having me. I'm privileged to be the business development director for Gross-Wen Technologies. We are an algae-based business technology that was born out of Iowa State University about 10 years ago. Privileged to be the business wastewater treatment seeing interest worldwide in what we're doing. Privileged to be a little bit about what that is. When you heard the term wastewater, you're probably thinking of when you flush the toilet, but it's a lot more complex than just that, right? So you're probably thinking of has a wastewater treatment plant, or most large communities, obviously. And we're receiving, those wastewater treatment plants are receiving wastewater not only from your home, large communities, washing clothes, washing vegetables, we're receiving those and flushing the toilet, but also car washes, all those industries that manufacture throughout the world. That wastewater needs to be treated before it gets released back to the natural environment. So it takes electricity, a lot of electricity, and I think I'll prove that to you here shortly. We also add chemicals, all sorts of different materials into those wastewater treatment plants to create clean water to be discharged. It comes with air emissions. We're creating a biosolids product also that needs to be discharged. So it is a very energy consuming process. This is a discharge. This is a typical wastewater treatment plant at probably a mid-sized community. You can see it's a series of tanks, blowers. Typical wastewater treatment plant at chemical addition equipment, drying equipment. Very very complex in some communities. Essentially, what we're trying to do in wastewater treatment, and this has been going on for 100 years. We've been trying to blow air into wastewater, and this is to create bacteria that will consume the organic material in that wastewater. Okay? Well, that bacteria is just like you and me. It requires a lot of oxygen, and it expels CO2 to the atmosphere. So we blow air into it continuously, 24 hours a day, 7 days a week, to the atmosphere, 365 days out of a year. In fact, for some communities, their government energy budget, which is comprised of, heating and air conditioning buildings, powering street lights, traffic lights, vehicles, all those vehicles that are out maintaining community facilities, and wastewater. Wastewater can represent up to 40% of a community's energy budget. That is a massive amount. In fact, if you think about greenhouse gas emissions, wastewater represents about 5%. That's 1/20. If you think about our total greenhouse gas emissions worldwide, massive amount. So we have a big problem and a big opportunity. Greenhouse gas emissions worldwide. This is a picture of Slater, where a big we have an problem. Installation, and this was their wastewater treatment plant prior to us getting involved. And so you can see in that top cell, so it's a 3-cell lagoon. Primary cell has a series of blowers blowing air to create that bacteria. Primary cell, and then it flows to the secondary cell, and then the quiescent cell before going to primary cell that is nearby. And then it flows to the secondary cell. They had 3 blowers at 75 horsepower each, blowing air 24/7. Flows before going. They also recently, the state recently gave them new permit requirements. So they were meeting their ability to remove organic matter from the wastewater, but they were not able to meet their ammonia limits. Ammonia is a form of nitrogen that is food for their ammonia limits, right? Ammonia in nature, food for their ammonia limits, creates algae blooms. Ammonia, algae blooms, food for Big Creek, along with phosphorus. Right? We hear about those on the news all the time, where ammonia, we've got a harmful algal bloom. No swimming. It's bad for aquatic animals, and so we're trying to get that ammonia out of animals, the streams before, or out of our wastewater before we're trying discharged to the environment. So as you can see, in the 3 years out of our prior to us getting involved, they were not able to meet their permit limits. Out of our wastewater, 3 years prior to, or is shown in red. Obviously, it's seasonal. It changes. Out of our waste, summer and winter. The limit 3 years prior to conditions. Obviously, it's they were not able to meet it. Out of our waste at certain times. The limit summer and winter. So a little bit about what obviously it's seasons. The limit in times during the summer and winter. Like I said, 10 years ago. So a little bit about what treatment the limit in times to during the invented nitrogen and phosphorus, because those are valuable. So a little bit about what that everybody needs to recover growing plants, right? Because those are valuable, able to reduce the energy required to recover to treat that wastewater, and we're because those are valuable. I mentioned required bacteria expels CO2 to the atmosphere. Algae, as a plant, does exactly the opposite. It consumes CO2 to the atmosphere, releases oxygen. Exactly the opposite. Sorry, it's going.
Today we're in our research and development facility just outside of Boone, Iowa. It's a greenhouse that allows us to test our system on various wastewaters and how we can manipulate the algae to grow in a certain way that would maximize treatment, or to maximize the effectiveness of the end-use product that algae can be turned into. This is the science behind what we do. We're at a smaller scale. We're treating different wastewaters to see how we can better the system, improve wastewater treatment, and also improve end use of that product. How we as can either a fertilizer, a bioplastic, a biofuel, or as a feedstock for how we can that I'm really excited about. We started with a pilot project in Slater. Then we moved to a full-scale demonstration project where we tested at a larger scale for over a year. Moved to a full-scale demonstration by the Department of Natural Resources. And now we have a full-scale installation where we're actually treating the city's wastewater by the Department of Natural Discharge requirement. So wastewater, and now we have a full-scale has been treated using actually treating the or chemical-based, and now we have those are typically more complex, very complex, energy consuming, chemical-based. You know, obviously require chemistry. Which can be chemical-based. Algae being Mother Nature's obviously require chemistry, which can be approach. Obviously require use algae to which can be from the atmosphere and deliver oxygen to approach. We use algae to consume 40% of it is on, based on wastewater treatment. That's a huge impact to community. We greatly reduce based on waste aeration that's required, and ultimately the 40% energy that is needed for that system. We now have full-scale installations with that equipment. We're learning a lot about the system itself and improving how installations with how it's installed and what our most viable applications are. We now see interest worldwide for what we're doing. Interest worldwide. Interest worldwide.
Maybe give you a high-level overview of what's actually happening on those belts that you saw in the video.
Interest worldwide.
So in position number 1, when the belts are rotating, when they're in the water, they come in contact with. So in position number 1, phosphorus. When they come out of the water, they have access to an atmospherically
phosphorus,
available CO2. When they come out,
interest worldwide.
That's our energy source. And so
atmospherically
number 3, we basically
when they come out,
interest periodically, take the algae and turn it into a useful
atmospherically. When they come out, interest.
So that's what the algae looks like close up. Atmospherically a useful product.
Interest.
Basically, what we're doing
so that's
is
what the
atmospherically
a useful
product. Belts using a scraping mechanism.
So that's what the
useful product. High productivity in a low or a relatively
mechanism.
Low, footprint,
a useful product
because we're going vertical.
Productivity mechanism.
Here's a quick.
We're going vertical. Productivity.
I don't know if this is going to show as a video. That's basically what it looks like when we're scraping the belt to harvest that algae. We're removing the nitrogen and phosphorus that gets absorbed into the material or into those cells, and that's how we're removing nitrogen and phosphorus from the wastewater. So this is a depiction of
that's how we're
a 10-belt module. We build these
and that's how we're
modules. Each module has
a 10
one
belt
5-horsepower motor, and then we have a couple additional fractional horsepower motors.
Each module
used to drive the
and then we have a couple
mechanism. It might be kind of hard to see, but there's a
each
drive
module
shaft that goes across the entire face up top.
and then we have a couple
The entire face of
might be
the
kind of hard to
module.
see, but there
And so one motor can drive
Face
that
up
whole
top.
mechanism or series of belts.
might be kind of hard to see, but there one
It's very
motor
modular.
can face up top.
So depending on how much material you need
One
to remove
motor
from that
can
waste, and it's a
water.
very modular.
We can
system. Grow our
face up
system
top.
to meet the needs of a community or an
One
industry.
motor can
This is actually a
we
depiction
can
of
face
a
up top.
Large a community or an
One motor can face up top
of a state of Washington, where we're removing One motor can face up top. Every single state of Washington. I mentioned we turn it into a useful product in the state of Washington. We can dry it and pelletize it and turn it into a fertilizer product. We can take algae and turn it into the soles of your shoes. And dry it and pelletize. We're working on a soil amendment product where we can take algae and turn it, put into the soil. Now dry it and pelletize carbon that we consumed from the atmosphere and puts it. We can take algae and turn it, and also delivers micronutrients to plants and puts it, if you're using industrial-based fertilizers, can eventually strip those micronutrients from the soil. So we're improving soil health by using this product. Eventually, we also have an interesting partnership with a large oil by using this product to turn that eventually into sustainable aviation fuel. An interesting by using this product. Producer. So these are all the benefits. We're removing nitrogen and phosphorus. We're turning the algae into a useful product. It's a very low carbon footprint, low energy consuming, and carbon capture. All happening with wastewater treatment. I mentioned we have worldwide interest. This is maybe a little bit dated, but these are the projects that we're involved with currently. And carbon. So back to the Slater project, you can see that on the left side, our system was all built within the existing footprint of the lagoons. A little bit about the construction. The first cell was all drained down so we could remove and had to remove the sludge, the bacteria that had grown for 40 years was all drained and settled in the bottom. We had to have them drain that cell down and remove all that material before building. That's part of the dredging process before building. Then we filled in a portion of the lagoon, as you could probably imagine, before building. Pouring concrete. Then we, as you saw, our system is all within a greenhouse to allow naturally occurring sunlight to power the system. As you imagine, and here's our modules that have to be assembled in the basins. And then the virgin belts that are just being hung on the have to be assembled before wastewater is added. Governor Reynolds in the state of Iowa has been very supportive of our growth, and she obviously was happy to be at our ribbon cutting there a couple years ago. And proof is in the pudding. We're actually meeting those effluent requirements. You can see as we were building, they were well out of compliance. But once we turned on the systems, effluent requirements very consistently meeting their permit. Here's just an example of the interest and awards that we've been receiving for the imagination of our company's founders and the engineers that took a risk to put this system in place. So with that, I'm happy to answer any questions. Are there any questions online? I'm happy to. Yes. Yeah, great question. So it's a polyester weave made by a large textile company called Milliken. I'm happy to. And it's actually a material that's very reminiscent of another type of equipment that's used. It's prominently in the wastewater industry. Reminiscent of press. So when operators of our systems see that material, they're reminiscent
usually,
of,
fairly
and
accustomed
it's
to
actually, so
dealing with
when
that.
operant that's used, material, they're
Yes.
and it's actually, so when operating with that material, they're so when operating, yeah, when it's a fertilizer product, right, we have to meet when requirements for putting that material on the land, and
Right,
so
we have
to reduce the vector attraction for putting that material associated with
Right,
that material.
we have
So we have to call it time and temperature. We have to raise the temperature putting that material, right? We have to that material. So we have to be able to safely apply. Have that, to raise the temperature, right? We have to that material. So vectors. Ryan,
Phil, question from a
have
from a
to
member.
raise the
How
temp.
does the cost of one of these RAB systems compare to a more traditional system?
Yeah, thanks. I missed that in the presentation. So Slater had their engineer did a study where they presented multiple alternatives. Our system is
did a
typically about the same as another system. Typical. The same as technology that you would use to blow oxygen into the wastewater. Okay, so on a construction, the same cost, as we're about the same to blow oxygen. Where we really shine is when you analyze the 20-year or 30-year life to blow oxygen of that project to be in place. Is when you construction. That typical technology is going to consume a lot of electricity. Is when you be in place, and it's going to require some chemical addition. 30-year is when you electricity be in place. When you compare us to some chemical is when you electricity a lot of that, and lifetime. We're usually pretty successful. Some chemical electricity over a 20 or 30-year, lot of that. And any other questions? We're usually pretty electricity over a 20 or 30-year.
Mainly from the wastewater, or is it from the CO2?
We're usually pretty well. It needs all those things, right? It needs the nitrogen and phosphorus that's present in the wastewater over a 20 or 30 year. And it also needs it needs CO2 because it's a plant, right? All plants need CO2. And it needs the sun. So those are really the four elements. Right? All plants stay wet too, so it needs moisture to stay alive. So the four, right? All plants needs moisture to the four. Yes, I will say needs moisture without going into a lot of detail. We have interest from that industry. We'll say we're the four. Anything else? Okay. Thanks for the opportunity. We'll say we're